Hello everybody, my name is Stefan Bosse from the University of Bremen from Germany, and today I want to give a talk about IoT and edge computing using virtualized low-resource integer machine learning with a support for convolutional neural networks, artificial neural networks and decision trees. Towards learning technical systems. What's about? Tiny machine learning is a new approach that is being used for data-driven prediction, classification, regression on microcontrollers or embedded computers using mostly local sensor data. This is very important. But even simple sensor data acquisition, aggregation and processing is a challenge in distributed sensor networks environments, the IoT, mobile networks and other distributed strongly heterogeneous networks. So the goal is to process sensor data locally and derive compressed relevant information features like damages or attack patterns or whatever with final global feature fusion. So to overcome issues and limitations with software and machine learning deployment in strong heterogeneous computer networks, the real-time capable low-resource virtual machine REXA-VM is introduced. REXA-VM provides virtualization of basic machine learning operations and models, including, but not limited to, decision trees, ANN and CNN. REXA-VM and its ML operations can be deployed on low-resource microcontrollers like the STM32 ARM Cortex-M series, starting with 20 kilobytes of RAM only. So you see an example of a material integrated sensor node developed in our research group. And here you see it as very, very tiny device, 70 millimeters in square, with an STM32 microcontroller, with RFID communication, analog amplifying, power control, and so on, and a sensor here, and so on. So it's a very, very tiny system, and our goal is to implement machine learning or prediction, in this case damage prediction in materials on site on site the microcontroller. Host platforms and efficiency is a very important point, and efficiency of data processing is always objective to be optimized, especially for material integrated sensor networks as something like that. The efficiency of data processing systems can be compared by the following normalized performance factor epsilon, and it includes the data processing system's computational power in mega instructions per second, integer instructions per second, the memory capacity, RAM and ROM, kilobytes, the entire chip area, this is very important for such material integrated systems, and the electrical power is important too. This sensor node is powered by RFID. We have only 10 milliwatts of power supplied by this device. So it's very important. Here you see an overview of different microcontrollers and so on. And the ARM Cortex are very relevant series for such kind of microcontrollers. You see they all differ. And here, for example, the M0 is the most challenging device with only 8 kilobytes of RAM. Here in between we have the L073 device we're actually using in between, so we have at least 20 kilobytes of RAM memory. And you see the approximated or measured chip area. This is very important too for material integrated systems. So what's the concept? First of all, we have a virtual machine with an integrated compiler. This is very important. So the interface to this VM is always text format. Programs are always, and models like artificial neural networks or convolutional neural networks are always delivered in textual format. We have an on-the-fly compilation to linear bytecode, requiring only 600 lines of C code, very compact program. No dynamic memory management is required, except by stack operations. We have a very keep it simple and safe with less than 3,000 lines of codes, highly configurable, with a custom instruction set architecture and so on. The VM can be directly embedded in I/O loops in microcontrollers cooperating with other tasks. So here, short overview of the VM architecture. It's basically a stack-based processor with a VM loop, and here a time-based scheduled VM loop, mostly operating on one code segment. There is no heap. All data is always stored in the code itself. And here you see the bytecode compiler. Here we have the text input. compile this to bytecode stored in the code segment, and the text is stored in the code segment too, and is replaced in place by the bytecode, by the compiler. So it's very compact. We have a lot of interfaces to microcontroller services. Yeah, and basically here we have this stack-based processor. So if you're interested in more details, please read the publication. I here will go more have a focus on the machine learning part. Some words about the instruction set architecture. It is freely customizable, but most ops are zero operand instructions or single word instructions operating directly on the stacks or the program counter. Yeah, with some exceptions, the ISA can be freely defined by a software development kit. So, and zero operand operations consume only 1 byte. Yeah? So, and we have a stack processor, so you are free to provide a programming language. Basically, all programming languages can be compiled to a stack-based processor, but here we are using the classical Forth programming language with the reverse Polish notation. And you see it here. It's a little bit complicated to read, but it's Forth is both a high and a low-level language. This is very important. And so all our machine learning models and their parameters and so on are specified or programmed in Forth, or a customized version of Forth. So here you see one example. Here you see a very little tiny oscilloscope. It's just an example application for the Rexer VM. And here you see a dual use system with the scope application and the Rexer VM. It's the same device, but 2 different views. And this is used as a guided ultrasonic wave laboratory for the pocket. And here we implemented the Rexer VM with machine learning and so on the scope in our own firmware, but the scope can be purchased with less than $100 of costs. It's a commercial device. So we replaced the firmware with our Rexer VM and our own oscilloscope application. So you see one application. Yeah, but I will want to focus on machine learning here, and ANN and CNN computations required efficient and generic vector operations crucial to implement machine learning on microcontrollers. The Rexer VM provides a core set of vector operations that can be used for the computation of both artificial neural networks and convolutional neural networks. Training using classical error backpropagation is currently not supported on the device directly, due to the requirement of storing a suitable training and test data set on the device. And if we have only 20 kilobytes of RAM, this is a little bit challenging. If you have more RAM, you can perform the training on the device too. But actually, we train offline and transform the model to an integer-based arithmetic version and implement this on this, or execute this on this device. So, the core part of the vector operations, only integer arithmetic is supported, addressing the low resource and low power microcontrollers. Yeah, and an ANN and CNN consists of 2 parts, basically. The data, that means in this case the parameter, the input and output variables, and the structure and functions processing the data. So basically the ANN and CNN can be functionally decomposed in a vector and matrix operational chain. Yeah? Here is shown here. So we have a nested functional application. It's basically a functional chain. And you will see later some templates for ANN and CNN programs, and then you will see the linear chain of different operations. So the vector operations are central here, and ANN models can be decomposed in the aforementioned chained vector operations. And vectors are initialized arrays, in the case of model parameters, and uninitialized arrays in the case of input, intermediate, and output data. So vector data, I already said it, you saw it in the architecture overview. Vector data is always embedded in the code segment. There's no heap. Here you see the code segment, and this is a mix of bytecode instructions and embedded data. And the program code too has this feature too. We have instructions and we have data. So this is mixed, like a classical program. So here you see a summary of the vector operations. Again, if you're interested in details, please read our excellent publication. You find it in the proceedings. Yeah, and for and CNN models, a set of scaled vector operations is provided. Again, please remember that we are using integer arithmetic, but we originally train our models with classical floating point arithmetic. That means we have to perform a transformation from floating point to integer arithmetic with a scaling. And all these operations here support integer scaling. And there's one important feature. We assume, for example, we have 16 bits integer, signed integer arithmetics, but under the hood, we have a 32 bits integer arithmetic processor. So we can compute with double precision, but store data in single precision. Yeah. And the scaling parameters must be computed by a model analyzer. This is not a part of this work here, or this presentation, of course, part of this work, but not this presentation. And this is done offline, the transformation of the model. Yeah, you see different operations, vector scaling, addition, multiplications, folding operations used to perform a folding of an entire ANN fully connected layer, or vecconv, a multi-purpose convolution and pooling operation, mapping element application of a function, for example, the activation function, sigmoid function, and so on. And reduce is the vice versa, the vector reduction function, for example, minimum or maximum search, sum product, and so on. Yeah, the activations functions are really an issue. Linear functions have no x and y limits and basically no approximation error. We have to approximate floating point functions like a logarithmic function with an integer version. And this is really an issue because nonlinear functions pose an increased discretization error. And so we provide linear and nonlinear functions, but with lookup tables and interpolation. But here you see the issue with nonlinear functions. Here in the case of the sigmoid function, the red line is the floating point version, and the blue, it's very close, is the approximated version. But if we consider the error, this is really it depends really on the value where we are here on the x range. And the discretization error, of course, can be very high. Here, for example, on very low values. So the overall discretization error and approximation error of our networks, our artificial neural networks, CNN, depends on the value ranges and basically on the application of the network. A specific use case is important. Here you see an ANN template. It's just to give an overview here, and important is that the entire program consists of model data. Here the embedded, initialized, and here you see non-initialized data. The numbers are only placeholders, just examples. Yeah? And here we have an ANN with 14 input nodes, 8 intermediate hidden nodes, and 2 output nodes. Yeah, and here you see the forward activation function that is provided by the code, and this computes the input vector or maps the input vector on an output vector by using the aforementioned introduced vector operations. Details, again, can be found in the publication. For CNN, it's basically the same, and maybe a little bit more of data and a little bit more of operations, but we are using basically the same operations with except the vecconv operation, that is the generic pooling and convolutional function. Again, you find the details in the publication. Here I show just the pattern. But this is all. This is a CNN. This is CNN implemented in Rexer VM 4th. Some words about the software development kit. You can compile with some specifications, basically any instruction set architecture to any language. Here we target the C programming language, but any other language is supported, including hardware and simulation target. And this is done by a software development kit and basically database-based software development kit with a lot of compilers. And finally, you get C code, you get JavaScript code, WASM code as a WebAssembly code, or any simulation models that can be used to investigate the behavior of specific programs executed on the Rexer VM. I don't address it here, but read the publication, you find some more details there. Yeah, but last but not least, some use cases. We have two use cases, both addressing damage detection using time-dependent ultrasonic signals. I don't go in detail here, but here you see one use case. We have here basically 6 time signals from 6 ultrasonic measurements. Here you see a plate with ultrasonic transducers, and here waves are excited and here are measured, so we have a time-dependent signal. Then we have a method to derive specific features from the signal, basically by the Hull computation of the sensor signal, and finally stored to conventional classical ANN with 14 input nodes, 8 hidden nodes, and 2 output nodes. And the output is basically regression to give an estimation of a damage location here of x and y coordinates with respect to the plate we are investigating. So we have to perform feature extraction, and finally we applied this to the integer scaled ANN, and we get results comparable with the floating point application. But here I want to give the focus on another application. Using the CNN, damage detection with the CNN. It's very similar to the first use case, but here we have a multipath measurement. That means we have 6 independent measuring paths. They are measured sequentially. And here we have only one measuring path. Yeah? We have only one sensor, one time signal. And here we use basically a spectrum-based method representing the frequency space of this time-dependent ultrasonic signal as an image by using discrete wave transformation. And finally, we have an image that is used by the CNN. And here we have only a binary damage classification. And here I show some results. The original floating point arithmetic model, it was a very simple CNN with only one convolutional pooling layer and the softmax, fully connected artificial neural and softmax layer, very simple CNN. And the overall classification error is in the original trained floating point arithmetic model, it's only about 5%. I have to say that these signals are very noisy and we have a lot of distortion, so this is a very bad data set base. But we achieve still 5% or only 5% classification error. So the accuracy is more than 95%. The integer scaled and transformed Rexer VML model using the aforementioned introduced ISA, vector ISA, showed a classification error of 5% too. So we have no loss. Yeah, this is the same data set. But initial transformation only regarding overflow scaling showed underflow issues and high classifications error. So recalibration of the scaling factors and adaptation was required. But it's an amazing result. At the end, some performance results. First of all, some highlights. The machine itself has a friction of 1 to 70. For about 1 to 70, that means we require about 70 native machine introductions per virtual machine introduction execution on the ARM Cortex. We have a friction about 1 to 700 if we consider the compilation, the just-in-time compilation from text to bytecode. That means we require about 700 native machine instruction per word, per high-level program word. The energy efficiency is very high, or the energy efficiency. We require only 13 nanojoule per VM instruction, 130 nanojoule per word compilation for the ARM Cortex M0 Plus architecture. Yeah, and the computation times of medium-sized ANNs is below 1 second, typically in a millisecond range, and the compilation time of medium-sized programs is below 1 second, typically in the millisecond range. And the startup time of VM is very low, was below 100 milliseconds, typically in the millisecond range too. So very, very promising results. Here you see a summary of the dependency of the computational time, of the forward activation time of an ANN, depending on n. It's a linear dependency, of course, and you see here it's scaled on microsecond per forward per megahertz. This is very important. And still, if you clock your microcontroller with 1 megahertz, you are able to compute a medium-sized ANN in a computation time below 1 second. Yeah? And here you see the code size is typically below 2 kilobytes, even for larger ANNs. And here finally you see the code size, including the model and the forward function for CNNs. Here we have a n square dependency, of course, with a number of cells, but you see still even more complex CNNs can be stored in less than 10 or 20 kilobytes of RAM memory. And so to summarize, I introduced a stack-based virtual machine architecture for low resource, tiny embedded systems and showed some evaluation metrics. The overhead, even on very low resource systems, is low with respect to typical running times under energy constraints and tasks to be performed in real time. A major feature, not so highlighted in this talk, but a major feature is the tight coupling of text to bytecode compilation with the bytecode interpreter, ensuring robustness, security, stability, and interoperability in strong heterogeneous environments. Yeah, and finally, ML classification and regression models can be computed using integer arithmetic and a set of specific vector operations, or specific but generic vector operations with low computational times and memory requirements. Okay, thank you for your attention. You can download the slides here on www.edu-9.de. And if you have any questions, please feel free to contact me. Any questions are welcome. Yeah, thank you for your attention. Any questions are welcome.